First of all, I will give some brief introduction about the adsorption column. So, what is the adsorption column? This is an industrial equipment that used in plant, which is mainly used for gas absorption or liquid absorption processes. So, how does it work? It transfers one or more components of a gas phase into a liquid phase. It is achieved through contact between liquid and gases, so that the desired components will be selectively adsorbed. Here is the definition of the adsorption. It is also known as gas scrubbing or gas washing. It involves the transfer of one or more gas phase species into a liquid solvent. The applications are used to separate gas mixture, remove contaminants, and recover valuable substance. So what is the adsorption important in the plant? It is used to facilitate the separation and purification of gas mixtures, contributing to product quality and environmental sustainability. There are two types of absorption, which are chemical absorption and physical absorption. Chemical absorption refers to the reaction between the adsorbent and solute. However, for the physical absorption, there are no significant chemical reactions between the adsorbent and solute. Basically, there are two types of methods for gas absorption. Firstly, I will talk about the cold current gas absorption. By referring to the diagram at the right side of the slide, we can see that the gas and liquid are introduced from the same side of the column, which means that they are flowing at the same direction. However, this method is rarely used in industry due to their less efficiency. As the liquid flow and gas flow is flowing at the same direction, the pressure change between these two flows are slightly small, and it does not facilitate the mass transfer of the desired species. Besides, it also requires infinitely tall column to produce liquid and gas stream at equilibrium. Next, we will proceed with the counter current gas absorption. Based on the diagram, the gas is introduced from the bottom while the liquid is introduced from the top, which means that these two streams are flowing at the opposite direction in the column. The gas component A is continuously transferred from the gas phase to the liquid phase. So by moving out the column, there is a decrease in total gas flow rate and a decrease in concentration of A and in the gas phase. This is because the species A are continuously transferred up from the gas phase. By moving down the column, there is an increase in total liquid flow rate and an increase in concentrations of A in the liquid phase. So the liquid is absorbing the component A from the gas to the liquid. In the industry plant, the most common adsorption column used is the tray tower adsorption column and the back tower adsorption column. So for the tray tower, it consists of a number of trays which is used to contact the hot gas with the cooling liquid. So from the diagram, we can see that when the liquid is entering at the middle of the column and it is flowing along the surface of the stages, which are the tray of the column. At the meantime, when the vapor enters from the bottom of the column, and it will rise and pass through the holes of valve in the trays. And this process provides an intimate contact between the gas and liquid, which enables the adsorption process to occur. So there are different types of tray for the tray tower, which is the sieve, impingement, and valve. The characteristic of the tray tower is the various gases and liquid flow rates can be handled. This is more precise prediction of blade efficiency, provides stage-wise contact, and easy to clean when the liquid produces fouling or deposition of particulates. Next, move on to the back tower adsorption column. Different from the tray tower, the back tower is filled with large quantities of tower packings and tower internals. It has a simple structure and has a high filtering performance. Actually, the working principle of the back tower is almost the same as the tray tower adsorption column. The liquid enters from the tower top and is evenly distributed onto tower packings through liquid distributors and then flow down along the packing surface. When the gas enters from the bottom of the tower, it is distributed evenly through gas distributor device. So when the gas raises up against the liquid path through void of the tower packing, the gas and liquid will contact on the packing surface for mass transfer, which the adsorption process occurs. So there are different types of packings, which are the resid rings, cedar interlocks, and honeycomb. So the characteristic of the back tower adsorption column is suitable for low capacity activities. The column pressure loss is crucial to reduce temperature and pressure. And the back tower also facilitate low liquid hold up and keep the liquid and vapor phases in constant contact.
Let's compare the advantage of back tower and tray towers in absorption process. Back towers offer several benefits. They provide high efficiency per unit height, ensuring effective mass transfer. They have a lower pressure drop, reducing the energy consumption. Their flexible operation allows for a wide range of flow rates. Back tower feature a compact design, saving space. Additionally, they have a lower liquid holdup, which reduces the risk of degradation or reaction of the absorbent. On the other hand, tree towers also have their unique advantage. They are easier to clean and maintain, which is important for operation reliability. Tree towers ensure better liquid and gas distribution, improving contact efficiency. They handle large loads well, making them suitable for high capacity operation. Lastly, they offer a versatile design, adaptable to various process requirements. Next, let's discuss the disadvantages of back tower compared to tray towers. Back towers have some challenges. They are difficult to maintain and clean, which can be a significant drawback for certain operations. There is a risk of maldistribution, leading to inefficient mass transfer. They have limited capacity for handling large liquid loads, and the initial cost for packing materials can be higher. Tree towers also come with their own set of disadvantages. They have a higher pressure drop, which can increase energy costs. They offer lower efficiency per unit height compared to back towers. Tree towers typically have a larger footprint, requiring more space. They face operational limits at extreme flow conditions, making them less versatile for certain applications. Each type of tower has its limitation, and the choice depends on the specific needs of the process. Where are you going? Also, where are you going? Also, where are you going? Now I will be presenting a sample mechanical drawing of an absorption tower, specifically a tray tower used for gas absorption process. As shown in the diagram, this tower features a vertical cylindrical shell with a height of 20 meters and a diameter of 2 meters. The sides we have 30 trays spaced at 0.6 meters apart. These trays facilitates the contact between the gas and liquid phases. Key components include a liquid distributor at the top to ensure even distribution of the liquid absorbent, and a mist eliminator near the gas outlet to capture any entrained liquid droplets. For the streams, we have the feed gas stream entering at the bottom containing argon, oxygen, nitrogen, water, and acetone. The liquid absorbent, which is primarily water, enters at the top. After the absorption, the treated gas exits at the top with significantly reduced acetone content, and the enriched liquid exits at the bottom. This setup allows for the efficient mass transfer and absorption of acetone from the gas phase into liquid phase.
In this part, you'll learn on the procedure for tray tower sizing. The first step is that you need to extract the required data as listed here. Next, calculate the surface tension factor and grow ratio parameters using the formula given. The fourth step is you need to determine the forming factor. If the system is non-forming, the forming factor is set to be 1. If the system is forming, then you should assume the value of 0.5 to 0.75. Next, you can calculate the ratio of AD over AT according to the grow ratio parameters as obtained in step 3. And now you can determine the whole area factor according to the trap type of your system. If it is valve and bubble, then the whole area factor is 1. If it is sealed, it is generally depends on the ratio of AH over AA. If it is over than 0.1, then the whole area factor is 1. But if the ratio is between 0.06 and 1, Then the whole area factor need to be calculated by using the formula 5 AH over AA plus 0.5. Now you need to determine the capacity factor C, but before that you should deciding on the plate spacing and obtain the CCB from the graph. And calculate the capacity factor by using the formula given. Next, you should calculate the flooding velocity and the tower internal diameter. Note that the F is flooding fractions, which is typically 0.75 to 0.85. Next, you can estimate the design pressure and temperature by using the formula given. After that, you can estimate the maximum allowable stress by using the design temperature obtained in step 10. You should calculate the minimum wall thickness and assume the value for well efficiency, either 0.85 or 1. So before you calculate the height of tower, you should know the value for in actual height of sum below bottom tray, disengagement above top tray, feet tray spacing and skirt, and it can be obtained from Espen Plus or by assumption. Next, we can calculate the thickness to withstand the wind load by using the formula given. The following step is to calculate the final cell thickness. The average Verso wall thickness (TV) is calculated by adding up the minimum wall thickness and the thickness to withstand the wind load. So even for non-corrosive conditions, a corrosion allowance (TC) of 1/8 inch should be added. Next, you should choose the inclusive and sum the value given in the table with the calculated final cell thickness just now. Next, you can recheck the outer diameter by using these equations and calculate the percentage error between the initial DO value and the new DO value. So if the error is less than 5%, so the initial assumption of DO value can be used. And the final step is you can calculate the weight of the cell and two heads by using the equation given.
So next we will proceed with the example for tray tower. So in this case we take the example for 19.4 in a reboil absorber operating as a de-eternizer at 400 psia to separate a light hydrocarbon feed, and the condition at the bottom tray are given as below: liquid phase and vapor phase. And then if sieve tray are used with a whole area of 10% and 24-inch tray spacing, determine the tower diameter. Assume 80% of the flooding and a forming factor of 0.75. So next, we will calculate it using the Excel. So the first step is extract the required data, which is the liquid density, liquid molar flow rate, liquid flow rate, surface tension, vapor density, vapor molar flow rate, and the vapor flow rate. And then we proceed with the step 2 is the calculate surface tension. So we will calculate it, and then we proceed with the step 3 is calculate the flow ratio parameter. And step 4, we need to select the forming factor. So in here we need to insert forming system, and then the question given is 0.75. Then after that, select the AD over AT. So in this case, FLG is 1.23, so we choose the greater than 1. So after that, we select the whole area factor, which is with sieve tray with AH and greater 0.1. Then we need to calculate capacity parameter when the FLG is equal to 1.23 and the tray spacing is 24 inch. So based on the figure 13.4 is the CSV is around here, so 0.1. So after that it will calculate the capacity. So we proceed with the step 8 is calculate the flooding velocity. So after calculate the flooding velocity, we need to calculate we can calculate the tower internal diameter. So we need to key in the flooding factor 0.8. So after that we can get the final value is the internal diameter is 4.989 feet.
This part will explain about the sizing of the PEG tower. In the first step, we need to extract the required data shown below and calculate the glow ratio parameter using the formula given. For the next step, calculate Y using the Lever floating correlation while the density function is calculated using the formula given. Next, calculate the viscosity function. Take note that the viscosity function is valid for the liquid viscosity in the range of 0.3 to 20 centipoise for random packing of 1 inch or greater nominal diameter. For the calculation of flooding velocity, firstly choose the packing factor based on the type of packing in the table 13.1 and substitute the chosen packing factor into the formula given. After that, calculate the tower inside diameter and estimate the design pressure and temperature using the formula given. For step 9, estimate the maximum allowable stress based on the temperature calculated from step 8. Then calculate for the minimum wall thickness. The next step is calculating the height of the PEG tower. First, need to choose a HTTP value based on the condition and substitute the theoretical number of threads into the equation 13.9. After that, calculate for the wind load. Note that the outer diameter is the sum of wall thickness and the tower inside diameter. Step 13 is about the calculation of final shell thickness. First, need to add a corrosion allowance TC of 0.125 inch. Then substitute the calculated average vessel wall thickness TV into the formula given. For rounding up to the next increment, choose the inclusive value based on your plant condition and total up the value with the calculated final shell thickness. Next, we check the outer diameter. If the error is less than 5%, mean that the initial assumption of outer diameter value can be used. Lastly, calculate the weight of shell and tool heads using the formula below.
Next, we will proceed with the example for PEG tower. So in this case, we take example 19.6. Water is to be used to absorb the acetone from a dilute mixture with air in a tower PEG with 3.5 inch metal pouring. The average condition in the tower are temperature 25 degrees Celsius, pressure 110 kilopascal, and then the liquid phase and the vapor phase condition are given, and then they want us to determine the column diameter for operating at 70% of flooding. So for the step 1, because we require the viscosity of liquid and liquid density, so in liquid phase, it is a mixture, so it is very difficult for us to find the viscosity. To want to make it easy, we can extract the information from the aspen. So this is the information, okay. And then we proceed with the step 2 is calculate the flow ratio parameter. And then step 3, calculate the Y value. And then step 4, calculate the density function. And step 5, calculate the viscosity function. After we have Y value, density function, viscosity function, we can proceed with the step 6, which is calculate the flooding velocity. In this case, we need to enter the packing factor. So the question is pouring metal 3.5 inch. So the packing factor is 16. So we substitute all the information into this formula. Then we can get the flooding velocity. So after that, we can proceed with the last step to calculate the tower inside diameter. So after substitute all the value, the dt is equal to 4.30x7 feet.
Purchase cost of absorption tower can be calculated using the given equation, where Fm is the material of construction, and the table shows the value for material construction factor for pressure vessel and tower. CV is the cost of empty vessels including nozzle, manhole and support, and it is based on weight of shells and tool head, while CPL is the added cost for platform and ladder, which depends on inside diameter DI and tangent to tangent length of shell. CV and CPL value for horizontal vessel, vertical vessel and towers can be calculated using the equation shown as this slide, and it is associated with specific constraint and condition of weight W, inside diameter of vessel DI, and tangent to tangent length of shell labeled SL. The weight of shells and tool head in the cost correlation for pressure vessel of tower can be approximately calculated using this formula, where DI is inside diameter, TS shell thickness, L is tangent to tangent length of shell, and ρ is density of carbon steel, where 490 pound per feet cubic or 0.284 pound per inch cubic is used. For wall thickness, labeled as TP is computed from ASME pressure vessel code formula, where PD is internal design gauge pressure, S maximum allowable stress of shell material at design temperature, and E is fractional weight efficiency. Wall thickness up to 1.25 inch, value of 0.85 is used. For larger wall thickness, value of E is 1. This figure shows a curve for FOB purchase cost in US dollar, as for C index of 567 for vertical towers, vertical vessel and horizontal vessel, including the nozzle, manhole and support, based on the weight in pounds of the shell and tool heads.
As can be seen in the equation of wall thickness, TP, we need the information of PD, which is internal design gauge pressure, or design pressure, PD, in the unit of PSI gauge. As recommended by Sandler, the design pressure need to be greater than the operating pressure, which is P0. There are three cases, which is firstly, if P0 is between 0 to 5 psi gauge, then we need to use PD is equals to 10 psi gauge. Secondly, in the range of operating pressure P0 from 10 psi to 1000 psi gauge, we can use this following equation. And lastly, if P0 is greater than 1000 psi gauge, we can use a design pressure equal to 1.1 times the operating pressure. Additionally, from the equation of wall thickness, TP, we also need the value of maximum allowable stress. The maximum allowable stress depends on the design temperature and the material of construction. The design temperature may be taken as the operating temperature plus 15 degrees Fahrenheit. However, safety consideration may dictate an even larger difference. At a given temperature, different steel composition have different values for the maximum allowable stress. Furthermore, at low pressure, wall thicknesses calculated from the equation of TP may be too small to give sufficient rigidity to vessels. Accordingly, the following minimum wall thicknesses should be used as the table in the right-hand side. On the other hand, the equation of wall thickness TP is suitable for calculating the thickness of a horizontal pressure vessel, but does not account for the effect of wind or an earthquake on a vertical vessel or column, and is not applicable to vessels or column under vacuum. Therefore, the average wall thickness TV is introduced for determining the average wall thickness of a vertical vessel or tower to withstand the internal pressure at the top of the column and to withstand the wind load or an equivalent earthquake, in addition to the internal pressure at the bottom of the column. The simplified equation is as follows, where TW is the necessary thickness in inches to withstand the wind load or earthquake at the bottom of the column. The term 18 in the equation of TW accounts for column cage ladders. The average vessel wall thickness, TV, is then computed from the average of the thickness at the top, TP, and the thickness at the bottom, TW. Therefore, TV equals to TP plus TW. For the former alternative, there are present a method for computing the necessary wall thickness, TE, based mainly on the vessel length to outside diameter ratio, and the modulus of elasticity, EM, of the metal wall. This method only applicable to TE over D0 less than 0.05, as given by the equation on the second row. However, to the value of TE, the following correction TEC must be added, where all variables are in inches. The total thickness for a vacuum vessel is then TV equals to TE plus TEC. The value of modulus of elasticity, EM, is depends on temperature with the following values for carbon steel and low alloy steel on the right-hand side table.
Purchase cost of the installed plate CT is calculated using this equation. NT is number of trays, FNT is factor of number of trays, FTT is factor of tray type, and FTM is the factor of material of construction. CBT is base cost, and this equation is for sieve tray SCE index of 567, and this equation is valid for tower with inside diameter from 2 to 16 feet.
Moving on to the next part, which is the purchasing cost of a pack tower. Packings for towers are classified as dump or structured. The total purchase cost of the pack tower CP is given by the equation of CP equals to the empty vessel equation plus the packings. The empty vessel equation in the green boxes has been discussed in the earlier part. Install costs for dump packing are given by several of the references in table 16.27, which was developed by taking average of those costs indexed to CE of 567 and adding some additional values from vendors, includes cost of 6 different dump packing and 5 different materials. Compared to dump packing and trays, structured packings offer reduced pressure drop, higher stage efficiency in terms of reduced height equivalent to a theoretical stage, HETS, and capacity in terms of reduced diameter. However, they are more expensive in dollars per cubic foot of packing and are not normally available in carbon steel. Accordingly, installed costs of a structured packings are not widely available. In the absence of a vendor quote and for a very approximate estimate, the installed cost of structured packing of the corrugated sheet type in stainless steel can be taken as $285 per cubic feet. In the absence of a vendor quote and for a very approximate estimate, the installed cost of a liquid distributor can be taken as $140 per feet cube of column cross-sectional area.
So this example contains both pack tower and tray tower. So we are first going to start with pack tower A1 and A2. So given the information of diameter, length, pressure of pack tower and also the material factor, as you can see from the calculator, this is the costing calculator. The information that we need is weight, diameter, length, as well as the material factor for the pack tower, which is here. We need to be inserted. So almost all the information is there except for the weight. So for the weight, we need to calculate using the sizing calculator, which has been explained by my friends from previous videos. So after having all this information, you can insert the values. So the costing calculator is connected to the sizing calculator, as you can see here. These are all information from the sizing calculator. So since we are gonna do a self-insert, we choose the self-insert option. So to make it easier to explain, I have put the calculator within the exercise page itself. So as you can see here, we can just input the weight or that we calculated, which is this, and then the diameter is 2, and the length is if I'm not mistaken 10 feet. So and then after we choose self-insert, since we are inserting our own value, it will be automatically calculated. Oh, don't forget to input the value of material factor. So the cost will be this. So since both A1 and A2 have the same parameter, the cost will be the same. So moving on to tray tower, it is also provided all the information here. So since we have all the information that we need, just input as we did for the pack calculator. So diameter 2, height 45, and then we have the 45, and then the weight. And also I have inserted all the necessary values here, and then the cost will automatically be calculated. So that's it for this example. yourself, and then choose